if a curved surface is such that every point on it, we are supposed to know, don't understand this. No, because it is defined like this. Every point on it is at the same distance from a point P. If a curved surface is such that every point on it is at the same distance from a point P, that same distance is R. And subtends an angle of omega steradian. The area of the curved surface is tell me, is R squared omega. If it is a sphere and P is the center, every point is at the same distance. Definitely, if a small curved surface, it need not be closed, such that every point on it is at the same distance from a point P and subtends an angle omega. It should be, that curved surface should be the part of a spherical surface of radius R having the center at P. You agree that? We are discussing fundamental. I expect you to concentrate a lot here. Whenever I say that if a curved surface is such that every point on it is at the same distance from a point P and the distance is R, it indirectly tells what? It is the part of a spherical surface of radius R having the center at P, correct? And subtend an angle omega. The area of the curved surface is R squared omega. But every point should be there at the same distance. Then only I can use that R squared omega or R squared d omega. Fine. Next. If a curve is such that every point on it is at the same distance R from a point P. It should be the part of a circle of radius R having the center at P. And subtends angle of theta radian, the length of the curve. Length of that curve is what? R theta. If it is d theta or d theta. This statement is talking about part of a sphere of radius r. Having the center at P. This set of points talk about part of a circle of radius r. Having the center at P. Know these things because radian and steradian are defined and given to us. Know it fully so that we can use it properly and get the advantage. Understand this? I will consider two lines on a plane angle it is. Suppose this is d theta. If this is dl, d theta, I'm talking about a line dl. This is at a distance, this end is at a distance of r1, this end is at a distance of r2. I can't relate r1, r2, dl through plane angle. If this is r and I consider a circular path of radius r, because this is d theta, this also appears to be a straight line. This is the part of a circle of radius r. If the angle between these two lines is theta, just for the sake of, no, let us say phi. Whatever it is. Projection of dl onto the radius of, onto the circle of radius r passing through that point is dl cos phi. Correct? Projection is dl cos phi. We saw that. Is equal to r d theta. Because it is a projection onto the circular path. We have to understand this as what? The length of projection of dl onto the circle of radius r. Both these lengths, whether you talk about this green arc or the red line dl, they are subtending the same angle d theta at the point P. I can use the plane angle only if every point on that curve is at the same distance from the point P. dl cos theta, or the projection of dl onto the circle is r d theta. The same way, solid angle d omega. If I consider some cap-like surface like this here, I cannot use the solid angle to talk about that surface area. This is ds. But if I project it onto the sphere of radius r and say this is the projection of it, every point is at the same distance r on this cap-like surface, which is the projection of ds onto the sphere of radius r having the center at that point. ds cos theta, here I just say theta. This is r squared d omega, which is equal to ds cos theta. Projection of ds onto the sphere of radius r will have the area at ds cos theta, now represented by r squared d omega, where d omega is the angle subtended by both these surfaces, ds as well as ds cos theta, same, at the point P. Now check Gauss law. Proof. I'll consider an arbitrary closed surface and a point charge of q coulombs at this point inside. Please see, at a point which is at a distance r from the point charge on the surface, I will consider a small differential surface. Please note that we are trying to calculate total outward normal flux through any closed surface. Total outward normal flux through any closed surface is to be determined. Check it. I considered a small elementary surface of area ds on the closed surface at a distance r from the point charge. Now, this is actually E bar equal to, at this point, what is E bar? Because of the point charge. In that direction, Q by 4 pi epsilon r squared. And D bar is along this direction given by Q by 4 pi r squared. Do you agree? D bar is in that direction. Things to understand properly and completely. Any doubt here? I told you that if at any point in the field of a point charge or any charge, D bar and E bar are the vectors in the same direction related through the permittivity of the medium. D bar is independent of the medium and E bar depends upon the medium. D bar is equal to Q by 4 pi R squared in that direction shown by the vector. I want to compute the differential amount of flux passing through this ds in the perpendicular direction because I want to integrate outward normal flux. The flux density is not perpendicular to ds here. Whenever I want to calculate the normal flux passing through this ds, I should take the normal component of d bar, multiply that with ds, correct? It is not normal. What is the projection of d bar onto normal if this is theta? Q by 4 pi r squared cos theta. D cos theta, correct? This is d cos theta in magnitude in the normal direction. Normal flux d psi n is equal to what? Q by 4 pi r squared cos theta into ds. Because I took the normal component into ds is the normal flux. Please check, it's only 2-line proof. Very, very important for us to learn this properly. D psi n, normal component of the flux through this differential surface ds that I considered. I am separating it now. This is the charge Q. In the figure, it is this ds. This is R. This is the direction of the field. This is the normal component. Listen carefully. Through this, if I basically draw a sphere of radius r, you're concentrating, right? I will draw a sphere of radius r. This is the angle subtended by this ds. End to end I took. Listen carefully. This is the cap-like surface of the sphere of radius r, to which this is radial to that sphere, normal to the sphere. This is normal to ds that I considered. The angle between these two is theta. Angle between these two is also theta because angle between two planes is angle between their normals. Check it. Because the angle between the normals is the angle between ds that I considered on the spherical surface. There, this is actually what? ds cos theta, which is equal to r squared d omega. Because this differential angle is d omega. Since ds cos theta is equal to r squared d omega, differential amount of flux passing through the surface normally is equal to Q by 4 pi r squared into ds cos theta is r squared d omega, because of which r squared get cancelled out. I will repeat the statement here. Now giving the statement before repeating. When I look at the differential amount of flux passing through the surface in the perpendicular direction, normal component of the flux coming out of the surface, R is getting cancelled out, because of which position of the charge is not important for me. Correct only. When you consider this ds, ultimately Q d omega by 4 pi will be the flux passing through it wherever the charge is there inside, because that R is not there in the final expression. R is getting cancelled out. See, position of Q is not important. It should be there inside, but wherever it is, if it is there inside, I know that Q coulombs will create this much of flux passing through the differential surface that I considered, which is Q d omega by 4 pi. What is the total flux psi n is equal to? Q by 4 pi integral d omega, which is the closed surface. On the closed surface, every total solid angle, integral d omega is what? Total solid angle subtended by the closed surface at any point inside. Integral d omega, we proved it to be equal to 4 pi, because of which it is Q by 4 pi into 4 pi, because of which it is Q. This is the proof. Now, if you can listen to me carefully and understand the subject here, you will see how weak the people who wrote textbooks also in this subject. Fundamentally, they are weak, because of which they could have just written. Some literature is there, they take it here and there, they collect and then write textbooks. Even the famous writers at so many points could not understand the subject properly. You will know. Maybe as communication engineers, we would apply this at so many points, because of which more you know in terms of number of subjects, you'll be able to teach this subject better, is what I feel. When R gets cancelled out in d psi n itself, the position of the charge is not important. One good thing that we did yesterday itself is that any charge Q creates Q coulombs of flux. If I keep the charge Q at the center of a sphere of radius R, if I keep charge Q at the center of a sphere of radius R, all the flux lines that are created by that Q will pass through that spherical surface in the radial direction, because of which entire flux is straight away outward normal. There is no doubt about it. Q coulombs of charge will create Q coulombs of flux. If that charge is there at the center, the flux lines will come out in all the directions, and If I consider a spherical surface of radius r with a charge at its center, I am sure that all the flux lines are radial lines because they are coming from the center of the circle along straight lines. And the entire flux is outward normal. At each and every point, it is directly outward normal. Total number of flux lines created by the charge Q is Q. All are outward normal because total outward normal flux through this surface is undoubtedly equal to Q. Outward normal flux. It is a spherical surface. For you to appreciate the fact, let us now consider a point charge only. A hemisphere of radius R1. I'll come down. Another hemisphere of radius R2 having the charge at the center. You're supposed to appreciate that these are hemispherical surfaces, right? Closed surface only. One sphere, walls, another sphere of big, smaller radius. These two surfaces, no, this is a circular lamina, right? Front view of this will be like this, no? Inner surface, a bulge, then outer surface, like this. This is the area that we talk about here. When it sends the flux lines out, half will go to the right, half will go to the left. And to this vertical walls, it is tangential, normal component is 0. Half of the flux lines will come through this surface. The charge is not there at the center of this geometrical center of this closed surface, but still, through this hemisphere, bigger hemisphere, Q/2 flux lines are normal. Through this also they are normal. It is equal to Q/2 because Q coulombs of flux is created by this. Q to the right, Q to the left. Q upwards, Q downwards. Correct? No? Sorry, Q/2 upwards, Q/2 downwards, Q/2 right to the right. This is Q/2. This is also Q/2. Total outward normal flux is Q. It need not be there at the center, and the closed surface need not be sphere. If I integrate the normal component of the flux over the closed surface, that normal component of the flux is equal to the charge enclosed. Listen, what we speak about here is total outward normal flux. Is it vector or scalar? Scalar. Correct? Flux is scalar. Flux density is a vector. How to compute this? I have a closed surface integral. It's actually double integral, closed on a closed surface. Or surface, I'll just put surface integral, closed, a circle on it. Or, okay, let me put it like this. Double integral over a closed surface. Yes. D bar is the flux density at any point. Dot ds bar is the total outward normal flux. I told you. What is ds bar? ds bar, I told you in the normal coordinate systems only, is that ds in that coordinate system into an. Please see this. Try to understand. Because ds bar is equal to ds into an, d bar dot ds bar is equal to what? D bar dot an scalar ds multiple. What is d bar dot an if you want to actually calculate? Is a scalar of magnitude mod d bar into 1 into cos theta. I think I've shown only this, right? ds. I took d bar. I took the normal component d cos theta. How can I get it? This is the normal an here. D bar dot an is what? Definitely modulus of d into cos theta. Flux is scalar, charge is scalar. Charge is scalar, flux is scalar, whereas flux density is a vector quantity. Very, very important. Current is scalar, current density is a vector for me. Density. Flux density is a vector. Flux passing through it is a scalar. Always normal component it is, because of which d bar dot ds bar. D cos theta into ds only I took. This is d cos theta into ds I took. What is the d cos theta? D bar dot an mathematically, because of which it is or basically what you have to compute is what is equal to closed surface integral s of d bar dot an dot product, scalar product. In Cartesian coordinate system, dx ax, correct? Dx ax plus dy ay plus dz az dot normal vector is what? Lax cos plus may plus naz, normal unit vector. Lmn are the direction cosines of it, right? Unit vector it is. So what is the dot product of it? Dx into L cos theta cos alpha plus dy into m plus dz into n in general. This is being integrated ds. This is a scalar into ds. That is integrated. I told you, right? A function being integrated on a surface. Integral of a function over a surface is what we are looking at here. Is equal to what? We proved that statement is what? Total outward normal flux through any closed surface is equal to the net charge enclosed by the closed surface says what? Integral over the closed surface d bar dot ds bar is equal to q is the net charge. Q. What is this Q? If inside the closed surface there is a point charge with Q1, there is a point charge with Q2, positive, negative, it can be anything. There is a point positive charge Q3. There is a line charge of length L1, rho L1, line charge of length L2, rho L2, surface charge of area A1, rho S1, surface charge of area A2, rho S2, volume charge of volume V1, rho V1. Wherever it is, doesn't matter. Total flux emitted by this system of charges is equal to net charge. I told you. If one is positive, if there is equal amount of positive and negative charge inside, what will happen? Positive charge creates so much of flux lines. And all the flux lines will go and terminate on the negative charge present in the volume itself. Even if they go out, ultimately they come back. Because of which net outward normal becomes equal to 0. That's what I have shown when I was sketching the field lines and seeing the structure of the field. What is this Q in this case? Q is equal to Q1 plus Q2 plus net charge means is this. With signs I have to add. Algebraic addition it is. With their signs I have to add. Q1 plus Q2 plus Q3 plus integral rho L1 dl plus integral rho L2 dl plus integral rho L3 dl. These line charge densities can be positive or negative. On L also, somewhere positive, somewhere negative. I'm not worried about it. That's why integral. Plus double integral of rho S1 ds plus double integral of rho S2 ds. Surface charges. Plus triple integral of rho V1 dV plus triple integral of rho V2 dV. This is all net charge when you call it. Algebraic sum with their signs of all the charges that are present inside if it is discrete set of charges. Very, very important case for us to get into mathematics and divergence theorem is this. If the charge is present everywhere inside the closed surface, it is called as volume charge. Then what is this charge inside? Triple integral of rho v dv. Every this over the volume enclosed by the enclosed by the closed surface. Check it. It's very, very important point about it is passing through. Integral d bar dot ds bar ultimately in this particular case. In the specific case, integral over a closed surface d bar dot ds bar is equal to triple integral of rho v dv. This is divergence theorem for me. One is surface integral, another is volume integral.